And you will get a link to this recording. It doesn't automatically record unless you click on a button on my end, so I have to remember to do it. Alright, let's see. Number 4. A bicyclist is riding on a path modeled by that function where x and f of x. Same problem. What's the rate of elevation change at x equal 2? What kind of function is that?
That's a linear function.
Exactly. So f prime of x is equal to what?
Just 0.08.
So what is the rate of change at 2?
0.08.
Exactly. It's 0.08 everywhere on that curve. What is that? It's the slope of that linear line.
Which doesn't change over time.
Exactly. No matter where you're at, how many seconds, you're still moving forward at 0.08 per second. So, all right. Look at 5. Let's see. What do I got going on here? How do we get rid of this?
Oh, I didn't link the whole page. I only linked the top part of it. I have to take screenshots of it because the way she has them online, you need a login to get to it, so I can't just send you the image, so that's just the screen cap I took.
Okay, let's go to 8. Is that alright?
Yes, 8's fine. This first lesson doesn't seem to be too complex. I understand this first one.
Okay, good. Good. Use the rectangles to approximate the area. In fact, we don't need to cover these if you're real comfortable with them. By all means, let's go forth until we hit stuff that you want to cover.
So, here's the beginning of the next lesson. Is that one? I sent it through the chat.
Yeah, I'll click on it right now. Okay. Okay, limits. We want the limit as x goes to 4 of x minus 4 over x squared minus 3x minus 4. Well, what's the first thing you do when you try to evaluate a limit?
Take the derivative of it?
No, plug it in.
Oh, yeah.
Plug in 4 for x. Unfortunately, that produces 0 over 0, which is called the indeterminate form.
Yeah.
0 over a number is always 0. And in other words, 0 divided by 2 is 0, and 2 divided by 0 is infinity. So the only thing that presents problems is when we have 0 over 0, we don't know what that is without further investigation.
Yes.
What can we do to manipulate this function so that maybe we can evaluate it? It won't come up to be 0 over 0. How about we factor the bottom? Whenever you see a quadratic, think factoring. How does that factor?
That turns into x minus... It's been a while. X minus 4x plus 1.
Okay. One clue, when you're in calculus and you're given problems like this, one of these factors is going to be the numerator, x minus 4. So if you want a shortcut way of factoring it, just assume that x minus 4 is one of them, and then finding the other one is easier. Okay? So once we factor it, we can cancel that with that, and we're left with 1 over x plus 1 Now, as x goes to 4, this goes to 1/5. So our 0 over 0 turned into 1 over 5 after we factored it.
Yep.
Okay. Now I'm just looking at these tables here. I assume, I did it again. I assume that they want you to fill in this table also?
Yes. I think
Okay.
it's kind of...
You know how to do that, don't you?
Yes, I understand how to fill
In
that
other
table.
words, to figure out f of 3.9,
Plug in
well,
3.9.
yeah, and I could actually plug it into this. In other words, it's 1 over 3.9 plus 1. So that's the first one, whatever number that comes out to be. And then the second one is going to be that. The third one's going to be that. And the fourth one's going to be 5.001.
The tables just seem to be showing that the limit as x approaches f is somewhere between the 3.999 and the 4.001.
You got it. And in fact, it would be very easy to assume that it's 1 over 5. If this produces 1 over 4.999 and this produces 1 over 5.001, that's trying to point out that at 4 it would be exactly 1 over 5.
What?
All right. But you have been shown this way of doing limits where you factor? Surely they have.
Yes,
Okay.
I have been shown that way before.
Good.
I had forgotten about it, but now that you've shown me it,
That's okay.
again,
Let's try the second one real quick. What's x minus 2 over x squared minus 4 as x goes to 2?
Now when you factor that, you get the x minus 2. So then you would just factor the bottom again.
Okay, what does the bottom factor into?
X minus 2, x minus...
The bottom is the difference of perfect squares.
X minus 2, x plus 2.
There you go. That cancels with that, so we're left with 1 over x plus 2. Now when we substitute 2, we get a number, 1/4.
You get 1/4.
Okay?
So that seems... Those tables seem fairly simplistic.
Well, I'm not sure what they're... I mean, the tables are designed to point out to you that as x gets closer and closer to 2, f of x gets closer and closer to whatever this limit is. In other words, the first limit was 1/5, this limit was 1/4. So those tables are just going to demonstrate to you that that's what happens. But you don't really need those tables to solve this problem. If we solve them as limit problems like we've been doing, then they kind of solve themselves.
Which, the next worksheet after that seems to be giving you just the limits and asking you to solve them like we have been doing.
Okay.
Without the tables.
We can do that with this without worrying about these tables. I know you know what to do with these tables.
Yeah.
These tables merely require you to know what, how to handle plugging in numbers for x. In other words, if f of x is equal to this formula, then f of 0, you plug in 0 for x. Well, in this next one, again, all limit problems are only hard if it ends up being 0 over 0. They're never hard if it ends up being a number over a number, or 0 over a number, or a number over 0. All of those, you know exactly what that limit is doing. So the only difficult limit problems are 0 over 0. Have you had this one? Sine of x over x, the limit of that as x goes to 0?
I do not think I've seen that question.
This is a key limit problem. It's equal to 1. It's not particularly easy to prove. You almost need more calculus in order to prove it. But it's so vital to know that they kind of give it to you like it's a theorem almost. So you want to know what this is, sine of x over x. Notice that it's 0 over 0, obviously, but that 0 over 0 goes to 1. And there's lots of ways to prove it, but it's difficult at beginning calculus. So they just kind of give it to you and want you to accept it, which is fine. Memorize that. Know that sine x over x goes to 1 as x goes to 0. But this is a different problem here. We're taking the limit of this as x goes to 0. Notice we're going to have square root of 6 minus square root of 6 on top, 0 on the bottom. So it's 0 over 0.
Yeah.
Well, what can we do to this? Because we can't really factor this. In other words, some of these can be solved by factoring, some can't. When you see radical signs, think multiplying by the conjugate.
Oh, yes.
Now, I can only multiply a function by 1 without changing its value. So if I multiply the numerator by the conjugate, I got to multiply the denominator by the conjugate also. Okay? And it's not immediately clear why that's going to help us, but it does. Notice that when the reason I multiply by the conjugate is because I'm going to eliminate any middle term.
Yeah.
In other words, if I have a plus b times a minus b, I don't have any middle term. I just have a squared minus b squared. Well, same thing with a radical, like this. Once I multiply these numerator by this numerator, I'm going to get this left term squared, which is x plus 6. And I'm going to subtract this term squared, 6. The bottom becomes x times x plus 6 plus x root 6. So this is the same thing as my original function. So all I've done is multiplied it by the number 1. Well, notice that we no longer have 0 in the numerator. That's great. Well, hold it. We do still have 0 in the numerator. We're going to have 0 in the denominator too. Huh. I wonder if they gave you this one, because this one almost requires these tables. This is a difficult limit problem. I thought I was going to solve it by multiplying by the conjugate, but after I've multiplied by the conjugate, I end up with x over x times square root of x plus 6 plus square root of 6. And now, if I plug in 0, I still have 0 over 0. So I haven't gained anything.
Yes.
In other words, she may want you to solve this by filling in this table to give you an idea of what it is. Because this is a difficult limit problem to solve. I might have to think about this for a bit before I could solve it.
Looking at her answer key, she got 1 over 2 root 6 as the actual limit.
Oh, of course. What was I thinking? I looked at this and thought we still had 0 over 0, but we don't. The x's cancel, just like in the factoring problem. So now we have 1 over this, and when you plug in 0 for x, you get 1 over root 6 plus root 6, which is 1 over 2 root 6. Sorry,
Yes.
I had a moment there. It's been a while since I've done limits. But, yeah, everything I did was correct here. It's just that when I got to this final step, I forgot to cancel the x's.
Yeah, I understand that.
Like I was able to in the last problem. And once you cancel the x's, you no longer have 0 over 0. You have 1 over whatever you get when you plug in 0 for that. All right. You cannot touch anywhere on this thing without it opening up another window, can you?
For next week, I'll try to find a better way to get them to you, but I wasn't sure.
Oh, this isn't bad. This is actually pretty good. As long as I can read them and... Okay, let's do this one. As x goes to minus 5, makes the denominator 0. What's the numerator?
The numerator will be the square root of 1 minus 3.
Actually, the numerator, if I plug in minus 5
Oh,
for
sorry.
x,
No, it's 3 minus 3, so it's 0.
so it's also 0.
Yeah, I
Again,
didn't realize.
no, I thought it had to be, unless they were going to mix us up here by throwing in a constant.
I missed the negative in front of the 5, so I put in just base 5.
Okay. So, again, this doesn't appear to be a factoring problem, but again, we can multiply by the conjugate. So what's our conjugate going to be?
Root 4 minus x plus 3.
Yeah. And the numerator becomes what?
4 minus x minus 9.
And the denominator, for the moment, let's just leave it in factored format. So what's the numerator become?
The numerator it's still 0.
Well, I mean, if we simplify it.
We get negative 5 minus x.
Which is... Which relates how to part of the denominator?
It's related to the x plus 5.
Okay. And in fact, if I put an extra negative sign in front of that, I can change the sign on both of those.
Yes.
Now I'm going to be able to cancel it out with this x plus 5. And my answer is going to be minus 1 in the numerator all over this part. Square root of 4 minus x plus 3. So now, when I plug in x goes to minus 5, I don't get 0 over 0. What do I get?
We get negative 1 over 6.
Uh-huh. And that's our limit.
Negative 1, 6. Okay.
Okay. You might want to check your answers as we're doing these just to make sure I haven't made a mistake.
She's at negative 1/6, and it makes sense to me why it's negative 1/6. So.
Okay, cool. Okay, let's look at 5. I can't quite make out that function. Can you?
It is on top. It's the square root of
Hold on,
4
hold on.
minus. Oh,
One
no, sorry,
second.
wrong
Just
one.
1 second until I can get a page open here. Okay. Square root of 4.
So I was read the wrong question. It is in brackets 1 on top. 1 divided by x plus 1. And the x plus 1's in parentheses. And then it's the end of that bracket. Minus 1/4 over x minus 3. The whole thing over x minus 3. And it's at the limit as x goes to 3.
So we plug it in, we got 1/4 minus 1/4, or 0, over 0.
Yes.
Okay? Well, if you weren't familiar with how to do these, you might be tempted to try to find a common denominator in the numerator and do that subtraction. But since we know how to do these, let's just do it. Let's multiply by the conjugate.
Okay.
See what happens. It's a little bit more complicated conjugate than we're used to, but we still know what our new numerator is going to be. What's the new numerator going to be?
The new numerator will be 1/4. The 1/4 turns into 1/4 squared, which is...
What's the left term?
The left term is... Well, I'm really spacing how to do that.
Just 1 over x plus 1 squared.
Yeah. Yeah.
And the right term, in other words, this is difference of squares.
Yeah. Yes.
Right?
16.
In other words, if I wanted to factor this, it would factor,
Back to that.
if I had this squared minus this squared, it would factor into this. So
Correct.
we're starting from the other direction where we already have it factored. It's easy enough to multiply it together without having to go through a lot of arithmetic by just putting it back into difference of squares. Okay, and then on the bottom, we've seen that we don't really need to multiply that out. You think about this for a moment. If I plug in x equals 3 into this, what do I get?
If you plug x equals 3, we get 1/4 squared minus...
Oh, you know what? I got my parentheses down here wrong. That's why I got to have parentheses around that. And that makes a difference. Forget what I just said.
Okay.
I'm thinking as to why this is tough. You do need to add these two in the numerator together. Let's expand this. In other words, I can't see anything that cancels at the moment.
Yeah, neither can I.
Okay? But if we expand this, we'll see it. That's 1 over x squared plus 2x plus 1 minus 1/16. In other words, if I can turn this into x squared plus 2x minus 15, I'll factor it, and one of those factors is x minus 3.
Yes.
So, let's find a common denominator. There it is. And this top term is 16. And this term over here is x squared plus 2x plus 1. And that's where we're going to get our numerator. Yeah, our numerator is now going to be minus x squared minus 2x plus 15 all over 16 times x squared plus 2x plus 1 all divided by this denominator, x minus 3 times 1 over x plus 1 plus 1/4. One thing I forgot about calculus is you need to leave lots of room. Okay. Now, our numerator, let's take a negative out of it, and it's going to factor into x plus 5 and x minus 3. You see how that is equal to that? Okay.
And then we have an x minus 3.
Yeah. Let's see. They're both over this. And this, I'm only going to write this part of it because this cancels. So I'm going to write 1 over x plus 1 plus 1/4. Let me put that x minus 3 back in there for a moment. Yeah, as long as you have a fraction made up of two fractions and the numerator is the same.
Yeah.
You can't just cancel it. That's over 1. So if I wanted to divide this fraction by this fraction, I would flip the bottom one and multiply. My x minus 3's go away, and I end up with minus x plus 5
Oh.
Let me think for a second here. And also on the top, I guess I got to add these two fractions also. Hold on, let's go back a step here. I kind of got lost in my... Okay, let's see. If I add those two fractions there, I get 4 over that, and I get x plus 1 over that. Okay, so let's rewrite exactly what we have here. I have minus x plus 5. Oh, we better use that x minus 3 before I get confused with it. And we're going to have that divided by this. And instead of dividing, I'm going to multiply by the reciprocal of this. Let's see, that was 4 plus 1. It is now 4. And it's in the, oh man, let's see, that is x plus 5 in the numerator. So all of that's going to be in the denominator. I might have made a math error here, I'm not sure. But let's take a look at this. So now it appears we can actually cancel out two things, which is a bit strange. I don't remember ever doing that before.
Yeah.
So I got minus 4x minus 4 in the numerator. And in the denominator, I got this. There's no way the denominator is going to 0, is there? Let's see, what are we going to here? We're going as x goes to what?
3.
3. So as x goes to 3, the numerator goes to minus 12 minus 4, that's minus 16. The denominator goes to 16 times 9 plus 6 plus 1, 9 plus 7. So our answer should be minus 1 over 16.
Which is what she got.
Thank goodness. That's one of the harder ones I've seen in terms of limit problems. In terms of the algebra, the limit problems are all about hard algebra, is what they're about.
Yeah.
Especially when you have to multiply by the conjugate and you're multiplying fractions by the conjugate.
In the end, I understand how we got to the solution, though. So.
Good. That's what's important. All right. Let's see. What else do we got here? Here we go. Limit of sine x over x. I realize I skipped number 6, but I think number 6 we're going to do. 6 we're going to do the same way we did 5.
Yeah.
I'm going to multiply by the conjugate. 7, however, is one that we don't have any techniques to do at this point, other than doing this table. If you fill in this table, you will realize that as we get closer and closer to 0, our limit gets closer and closer to 1.
Yeah.
However, in terms of proving to you that that limit is equal to 1, there's only one other technique I know how to use, and that's L'Hopital's rule. Are you familiar with that?
No, I am not.
Well, they don't teach this to you until much later in the calculus course, and I'm not quite sure why. I guess it's because that when you first get limits, you haven't had derivatives. But L'Hopital's rule, I might as well tell you about it now. If you have a situation that is indeterminate, like this is, L'Hopital's rule says that if you take the derivative of the numerator and the derivative of the denominator and reevaluate it, that'll give you your limit. Well, the derivative of the numerator is cosine x. The derivative of the denominator is 1. And now if I reevaluate it, cosine of 0 is 1.
Then it becomes easy.
Very easy. And if you still get 0 over 0, L'Hopital's rule says you differentiate top and bottom again until you get a number or infinity. And eventually it will come down to something that is not 0 over 0. Now, part of the trick in teaching calculus is teaching people how to do that, because you haven't had differentiation yet. So you don't know about taking the derivative of a trig function. And this doesn't evaluate nicely by any algebraic techniques. You could probably find the proof of this in a calculus book, but it's a very complex proof. I have seen it before, but it's not anything like what we've done in the first 10 questions we've gone over. And so that's the point of these tables, is we don't have any other way of doing this problem, but if we fill in this table, we will realize that, right, this is probably going to be 0.999, this is probably going to be 1.01 or something like that, and you'll realize that as we get closer and closer to 0 for x, f of x gets closer and closer to 1. In fact, in my calculus book, when they first introduced this problem, they show you the graph. If you look at the graph of that, the graph looks like this.
On the graph, it's pretty evident.
Huh? Yeah,
on the graph, it's
exactly. The graph makes it real clear that as x approaches 0, sine of x divided by, the y-axis is actually sine x divided by x, and that number is 1. But that's actually not proof, believe it or not. In other words, in my book, when they give you this problem and they show you the graph, they say the graph suggests that the limit is 1, but it's not proof. And we're not quite ready for proof yet. Even L'Hopital's rule is not proof. Even though L'Hopital's rule is a theorem that has been proven, and we're certainly able to use it in this case, but in your case you haven't had it yet. So there is a far more complex proof for doing this. I don't think that's what they want you to do, and I don't remember how to do it anyway. The other very important trig limit that is this one here. That is another one where they don't give you the tools to solve this. That's equal to 0. Notice that we have 0 over 0 if we plug it in directly.
Yes.
Now let's apply L'Hopital's rule. Derivative of the numerator, and remember when you're applying L'Hopital's rule, you do not use the quotient rule. It isn't the quotient rule. It's the derivative of the numerator divided by the derivative of the denominator. Well, the derivative of the numerator is minus sine x all over 1. That's 0. Over 1, which is 0.
Yeah. That was the last table on the page.
Well, and we're over our time. I just glanced at the clock. I love calculus so much that I can't even pay attention to time when I'm teaching. So I'll let you go.
Thank you.
We'll call that a session. Let's see. Is this going to be a regular time, I think?
Yes.
It is, right? Let me just make sure that
Yes.
next week and the week after you're still in there. Yeah. Okay. Good. Okay. So we're going to do just out of curiosity, is one session a week going to be enough to get you caught up in time for when you need to be caught up by?
Well, I think so. With this session, we covered almost all of Chapter 1.
Okay, good.
So if we have another session as productive next week, I think it should be just fine to get us...
So in other words, if we can cover these first 3 chapters in 3 sessions,
Yeah.
that will put you in a spot where you can pick up with chapters 4 then?
Yes.
Okay, good. Okay, sounds good.
Okay.
Chase, I will speak to you next Saturday. I will also, this email address is yours, right?
Yes,
Cash
that
on?
is my email address.
I've recorded this. Unfortunately, I didn't hit the record till halfway through, but I got a half hour of it recorded. I will post that on my website page. That's just a private page for you. I will send you a link to that page so that you can review these whenever you want. Every time we have a session, I will post it to that same page, and I will send the envoys to LA Dragon.
Okay. Thank you.
One of the few email addresses I can actually remember. So,
Pretty unique.
yes, it is. That's a cool email address to have, actually. I will. I'll talk to you next Saturday at 2. Oh, and next Saturday, Chase. Where do you want me to? You want me to just email you the meeting ID number like we did this time?
Yeah, that'll work just fine.
And your audio should be fully set. In other words, it comes the first time defaulting to telephone, but once you change it, the next time you pull it up, it'll be on speaker, mic and speakers. So I won't need to talk to you. The only thing I'll need to do is email you the meeting ID number, and then we'll be meeting. Once you get into the meeting, we'll have audio.
Okay.
Talk to you next Saturday. Have a good week.
You too.
Bye-bye.
Thank you.